Hello, my name is Arman Behnam. I'm a research assistant at Illinois Institute of Technology, PhD student in my second year, and this is the first year's output as graph neural network causal explanation via neural causal models. This paper is accepted at the 18th European Conference on Computer Vision 2024. I did it with my advisor, so today I'm telling you that in this paper we propose a causal GNN explanation method to identify the ground truth within a graph, meaning that you can see here 6 groups of graphs, and in each of them you can see some red nodes attached to a bunch of blue nodes. So those blue nodes are BA-shaped graph or tree-shaped graph in different sizes, and the red nodes, or the group of red nodes, are the nodes that we are looking for to find out. Like sometimes they're like house, and sometimes they look like grid in different sizes, and sometimes there are cycles. So this method should identify these group of red nodes. We name them as ground truth within a graph. But what are GNNs here that we are looking for them? So GNNs, or graph neural networks, are neural networks trained on graphs. The input is like a set of nodes, a set of edges, and also node features and edge features. So these nodes and edges have labels. So we can see on these labels as outputs, we can train some graph neural networks and get the results for node classification, which helps us predict the node label, or the graph classification, which helps us to predict the label of a graph. But what is GNN causal explanation that the method is working in this area? So consider this 4 nodes graph, A, B, C, and D. We want to know that if we want to predict a node label or a graph label for this graph, what will be the most informative node, or what will be the most part of this graph? We name that as causal subgraph. So if we want to do a causal explanation to find this information, we can see that the most important node can be A, which is attached to 2 nodes, B and C, and the links or the edges between these 2 nodes, meaning AB and AC, are more important. And with that, we can predict the label of this graph, or we can find the most important information for this graph. So here we want to train a model to identify the causal subgraph. So consider this causal subgraph. We can see that X has a direct link to Z and Y has a direct link to Z too. It meaning that X has an effect on Z and Y too. But when we want to study the effects on node Z and understand the information that this node Z is containing, we can see the variable, or the V, a set of observable nodes we want to study, which is Z. And the latent variables are X and Y, and we can come up with some function. For example, Z is a composition of X and Y. We can see 2 times X and plus 3 times Y gives us the Z. So Z is combined from X effects and Y effects. So with this, we come up with the CXGNN, the GNN causal explainer, which is a method. You can see the overall picture of how does it work here. So we learned that we have a graph G, that within a graph G, there is a ground truth we are looking for. So consider one of the red nodes as a green node. We'd call that a target node. So based on that target node, we came up with a definition of causal structure, which shows the green node as the target node. We want to study the effects on that, and also the first neighborhood and the second neighborhood as blue and red nodes, and each of them has an effect on the target node, you can see. And also we can see a link between the blue node, each blue node and target node, meaning that there is a meaning, there is a reason behind why we can see a link here and why we cannot see a link or edge between a red node, which is the second neighborhood of the target node, and the target node. So we want to study the reason of these. And there's a model in the literature named SCM, but it is for direct edges within a graph. And also we have functions that comes up with this. But for this structural causal model or SCM, we have to know exactly the value of the effect, so we can come up with a direct and exact function. But in most of the cases, in real world cases, we don't know the value of the effects. So we come up with the estimation of that. We call that NCM, or neural causal model, which estimates the effects, for example, on reference nodes. So here we customized this knowledge of SCM, and we came up with a new kind of neural causal model that can calculate the effects for each node in the graph neural networks, which is a completely new thing in the area of explanation. And it gives us at the end expressivity, or a measure that shows how much this node is important or how much this node is informative in this graph. So the neural causal model works like this. Consider we have the exact knowledge of how the environment omega works, and within that knowledge, we have a knowledge of what are the variables or something like that, and we can come up with the neural causal model, which are like a bunch of them that are estimates of the exact world, and each of them can have queries and functions that we can come up with them. So I call this one a graph neural networks neural causal model, GNN NCM. So here we had some definitions for this work to make it happen. The first one is the meaning of intervention and causal effect. You can see that the probability of changing in the node label, which is information, given the intervention of the nodes that we define the causal structure based on them, we call that the intervention and causal effect. What's the meaning of causal structure G that I defined previously, and we showed that. So it's the set of union of set of observable variables V, and which are based on the node labels, and the latent variables U, which you can see are the latent variables for node effects and edge effects. So what did we find in this paper? The first theorem we came up was GNN SCM, which is the true meaning of when we know exact functions within a graph neural network. As you can see in the set of F, for each node, we can have a function that consists of the other nodes that are having effect on that node when we want to come up with the logical value. But the node we want to study in that example was node A, so we want to focus on that node A. You can see that node A also, for example, if it's binary, it has two states, A1 and A2, and each of these states have an effect on the environment too. So we consider a latent variable for them too, like UA1 and UA2. So based on this, we came up with the GNN NCM, which is estimation of this structure, which it's more complicated than this. So the description of the formulation is in the paper. You can look into it. And so the third theorem was in the node explainability, which shows that how can we calculate the probability of each node label change based on intervention in the real world. So it would not be exhaustive search, and it would not be exact thing, because we don't have the information for exact node labels. And we come up with the way to calculate the probability over a different set of scenarios for different node labels and different set of neighborhoods and different causal structures. And at the end, each explainable node has an expressivity measure, which is the accumulation of the node label times the possibility of that node label for all of the possible node labels we have in a causal structure. You can see that it's been measured for each NCM M hat with respect to the causal structure G and the parameters for that model. In the real world data sets, you can see that it outperformed most of the, GNN explainers. The GNN explainer, PGM explainer, guided backpropagation, GEM, RC explainer, and Orphic X are all outperformed in the real world for the two cases that we have the knowledge of the ground truth in the chemistry, like benzene and FC molecules. My future work are, I should say, point out that it's in causal representation learning as a line of thought for this, which in that we are searching for non-parametrically causal invariant identification with respect to interventions. So what does that mean? It means that we want to generalize representations of data based on perfect or imperfect interventions. And the second line would be the out-of-distribution generalization, meaning that we want to solve the distribution shift robustness challenge. And also we want to redefine this problem with respect to causal latent variables. Thanks for your attention.